Hello, everyone. Thank you for joining. So before I get into the research, I thought I'd start with a brief introduction of myself, especially since I'll be applying for jobs in the fall. Please feel free to skip ahead if you only want to hear about the research. So my name is Jason or Jaemyoung Lee. I'm a rising fifth year PhD student at the University of Pennsylvania, working with Masao Soko on Type 1a supernova cosmology. I'm part of the Dark Energy Survey as well as LSST desk. Within Type 1a supernova cosmology, I've been focusing on wavelength-dependent atmospheric effects. And for the Dark Energy Survey 5-year complete analysis, I've implemented corrections arising from these wavelength-dependent atmospheric effects. And more recently, I've started using one such effect, called DCR, to our advantage to measure redshifts of supernovae. First with LSST simulations, which is what I'm going to be talking about later, and also with real DES data. Apart from Type 1a supernovae, I'm also interested in some large-scale structure. And in LSS, I've been looking into BAOs as well as lensing of the cosmic infrared background. Now let's get into astrometric redshifts of supernovae. So this is a non-spectroscopic method of measuring supernovae redshifts, but different from photometric redshifts. This work was done with Masao, my advisor, as well as Rick Kessler at Chicago. Here is the archive number, so please feel free to check it out if you are interested. So I thought I'd start with a Hubble diagram to illustrate how important redshifts are for Type 1a supernova cosmology. So this is from the DES complete analysis, and you can see on the y-axis is the distance modulus, which is related to the luminosity distance, which has a dependence on cosmology. On the x-axis is the redshift, and in the Hubble diagram, we need the redshift of each of the supernovae that goes into the Hubble diagram. So you can imagine how important precise and accurate redshifts are for Type 1a supernova cosmology. So far, up until DES, we've always obtained redshifts of supernovae from spectroscopic in a spectroscopic way. So whether it's from the supernova itself or from the host galaxy. But Rubin is going to detect far too many supernovae, almost a million, probably about a million or so, for spectroscopic follow-up, which is why non-spectroscopic measurements are crucial, and there's a lot of effort for photometric redshifts that's been going on. This is where the astrometric redshifts come in. The astrometric redshifts are nearly independent from photometric redshifts. Also, these astrometric redshifts have already been shown to be useful for sources with distinct emission lines, such as quasars. And lastly, we do not actually need to do any additional measurements or observations apart from what we're already going to do to utilize these astrometric redshifts, although some moderate air mass observations will help. So the background behind astrometric redshifts lie in differential chromatic refraction, or DCR. Now, DCR occurs in our atmosphere because our atmosphere's refractive index is wavelength dependent. So this means that bluer or shorter wavelength light is refracted more in our atmosphere than redder or longer wavelength light. So if you were an observer on Earth, looking up into the sky at a blue and a red star that's located at the exact same position in space, it'll seem as if the blue star is located higher up. Now, the amount of DCR shift that occurs depends on the air mass or the amount of air along the line of sight. Let's break this down a little more. On the left, you're looking at the equation we use to calculate the DCR shifts, and you can see that it involves some integrals over the filter function and the source flux. In the middle here, I have plotted the supernova SED at its peak, as well as the LSST G band on top. On the top panel, this is for redshift 0, on the bottom panel for redshift 0.6. And as you can see, the overlap between the filter function and the source SED is different between the two panels. And this leads the astrometric shifts, the DCR shifts, to be different for redshift 0 and 0.6, as shown on the right. And you can see that at higher error masses, we see bigger shifts. Now, there's one caveat here, and the caveat is that because all the exposures in a CCD are affected by DCR, we're not going to be able to measure the absolute DCR shift. But what we can measure is the relative shift with respect to the average color star, because stars are what we typically use to build our astrometric solution. So this is why I'm plotting this figure with respect to the average color star. So you can say that the redshift 0 supernova is bluer than the average color star in the LSST G band, and a redshift 0.6 supernova is redder than the average color star in the LSST G band. Moving on to the methodology. So for our observed DCR shifts, we have been using SNe simulations. Now, SNe simulations is a software that's often used in Type 1a supernova community. And in these SNe simulations, we've implemented DCR as well as Poisson noise. And for the model shifts, we are simply taking the model SED and calculating analytically the DCR shifts according to redshift, air mass, color, and stretch for the LSST UGRIZ bands. And then we can calculate the chi-squared between the observed and model shifts for each of the observations for each of the bands for one particular supernova, and then add that all up to construct a PDF using the chi-squared. Then once we marginalize over C and X1, we can get our redshift PDF. We use two methods to obtain our astrometric redshifts to notice the DCR from now on. One is called CDF50, where we take the redshift corresponding to the 50th percentile of the cumulative distribution function as our estimated redshift, and PDF peak, where we take the peak of the PDF to be our estimated redshift. Now, there are advantages and disadvantages of either methods. On the left here is a case where CDF50 performs better, and you can see that the PDF is multimodal, but the higher peak does not correspond to the actual redshift. In the middle, we're looking at a case where PDF peak performs a lot better than CDF50, and you can see that here the amplitudes do not vary very much throughout all redshifts, but the highest peak indeed corresponds to the actual redshift. And on the right here, you're looking at a case when CDF50 and PDF peak both perform very well, and this is because there is a very distinct peak. Now, because we care about using these Type 1a supernovae for cosmology, we've imposed some selection cuts. So first, require that there are observations before and after the peak. And also, we have a signal to noise selection cut. And lastly, because we aim to combine with supernova photometric redshifts, and for the supernova photometric redshifts, we use a light curve fitter that fits for the light curve parameters and the redshift at the same time. We require that there's this LC fit plus C convergence. We also require that the fit probability is above a certain threshold. Here are the performance metrics we use to evaluate our redshifts. So first, the residuals are defined in this way. And here is the bias metric. Then we have an accuracy metric, the outlier fraction eta x, where x is typically taken to be 0.10. We also have a precision metric, or the MAD deviation. And when sigma MAD is farther away from 0, it means that the estimate is less precise. Now here is what our CDCR looks like by itself in a realistic scenario. So we're assuming that the systematic floor is 5 milliarcseconds, and that we do not know the exact epoch, so we're assuming realistic T observation, and also we marginalize over X1 and C. And when you look at these two panels, you can see that at the high redshifts especially, CDCR is not very good. And in fact, for CDF50, you see the streak here. CDCR is pretty much at 0.6 at the high redshifts. And this is because the PDF is so flat that the 50th percentile of the cumulative distribution function lies right in the middle of your allowed range, or redshift 0.6 or so. But when we zoom into the lower redshifts, or redshift 0.6 or lower, you can see that CDCR actually does pretty well. And these are the histograms of the residuals that reflect what I've just shown. And now let's move on to combining with photometric redshifts, as I promised earlier. So first, let me show you what host photometric redshifts look like. And you can see that it actually performs better at the higher redshifts, contrary to CDCR. Now, when we combine the two, this is what it looks like. So again, C host, then CDCR plus host. And you can see that the estimates have become considerably tighter, especially at the lower redshifts. But we also have the supernova photometric redshifts, again, obtained from LCFIT plus C. And supernova photometric redshifts, or ZSN, performs better at the lower redshifts, just like CDCR. But when we combine the two, we get tighter constraints throughout all redshifts, but more so at the lower redshifts. And we did not know a priori how independent CSN and CDCR were going to be, but it turns out that they are pretty independent because the correlation function coefficient is less than 0.2. Now this is CSN again, and now we combine with host photometric redshifts. This is what it looks like, and this is what happens when we combine all three. So again, CSN plus C host, and then ZSM plus CDCR plus C host. And you can see that combining all three definitely does the best, although you might wonder why it's not making it much better by combining CDCR. But what we later found was that adding the ZDCR information actually allows more candidates to converge when using this LC fit plus C. So this means that adding ZDCR recovers about 9% of the candidates. So in this figure here, there's actually 9% more candidates than the figure before, which is actually kind of remarkable, which means that we can use almost 10% more supernovae for cosmology, and yet still have better redshift estimates. These are the outlier fractions by the true redshift. What I wanted to point out was that combining all three does the best up until redshift 0.9 or so. At the highest redshifts, we can be a little smarter about selecting which candidates to combine the CDCR information for. The same goes for the bias and sigma mad. So here the bold symbols are bias values, and bold error bars are the errors on the mean of the bias, and the light error bars are the sigma mad. So same story here, up until redshift 0.8 or 9 or so, combining all three does the best. Here's a list of systematic effects we've looked into, and what I wanted to highlight here was that including all the systematics we do for the realistic scenario does not degrade the performance metrics by much compared to the perfect case or the ideal simulations without any systematics or statistical uncertainties. So what I just wanted to say was that we are limited by statistical uncertainties, not systematic ones. Before we end, I thought I would show you some preliminary results using DES data. And this is for one particular candidate, low redshift candidate. And let's focus on the left here. The Z-band average coordinate is what we typically use as the average color star coordinate because DCR is very small in the Z-band. And you can see that the estimated redshift is actually pretty close to the true redshift here, both around 0.2 or so. So what we hope to do is to expand this to many more supernovae. In conclusion, we've developed the methodology for type 1a supernova astrometric redshifts using DCR. We found that CDCR alone does pretty well at the low redshifts for LSST-like simulations. We also found that combining CDCR with C-host and C-SN, or photometric redshifts, substantially improves photometric redshifts. So we plan to implement these astrometric redshifts into the LSST type 1a supernova photometric redshift pipeline. And as mentioned before, we are starting to measure these astrometric redshifts using real DES data. Lastly, I thought I'd note that it's the first time astrometric redshifts were applied to type 1a supernovae, and we've constructed the full PDF for astrometric redshifts. And this work can also be adapted for other sources with distinct emission lines like type 2 supernovae. Thank you very much.